Hey everyone, Kevin here, new edition of Santa Rosa Junior College Wine Studies Online. This time a Wine 3 discussion of bonding, water, and ebulliometers. So let's get right to it. We talked last time about three types of bonding. We talked about ionic bonds, covalent bonds, and polar covalent bonds. Okay, so one was ionic bonds. Let me just review these three very quickly. So ionic bonds are between two ions. An ion is an atom or a molecule that has a full charge. And the example we used was table salt. There are two ions that bond in table salt, sodium and chlorine. And sodium has lost an electron. It's transferred over to chlorine. Remember, we looked at that video with the explosive reaction between solid sodium metal and chlorine gas. We transferred an electron. That's what gave off all the energy in that reaction. So we saw that big flash of light and heat during the reaction, and that created table salt, sodium and chlorine. And so those are attracted to one another because sodium has a positive charge and chlorine has a negative charge, and opposites attract. So we looked at that big matrix formed in a crystal of sodium and chlorine, and that's your ionic bond. So that's one. The second type of bonding we talked about was a covalent bond. And really we should break this down into two parts. Covalent bonds consist of nonpolar covalent bonds, or basically neutral covalent bonds with no charges. And that would be, for example, a bond between carbon and hydrogen. So we looked at methane a couple of days ago, a couple lectures ago, and then we reviewed it again this week. Methane would be CH4. So molecular formula is CH4, and the structure would look something like this. And each of these lines between carbon and hydrogen, each of those represents sharing of two electrons. And these are shared pretty equally. So this bond is neutral. This bond between hydrogen and carbon is pretty neutral. Likewise, this bond between hydrogen and carbon is pretty neutral. The electrons are shared pretty equally here in this bond. And that's true for all four bonds between carbon and hydrogen. So that's a nonpolar or neutral covalent bond. Then we talked about water, and those are polar covalent bonds. So these have partial charges on adjacent atoms. And the example we talked about was oxygen, it was water, right? So we have two hydrogens on an oxygen, H2O, right? So here's our molecular formula, H2O. And we talked about the fact that these electrons are shared slightly unequally. They're pulled closer to oxygen. So the electrons are pulled toward oxygen in each of these bonds. We don't break the bonds like we did back in an ionic bond where we actually transfer an electron from one atom to another. In this case, the electron density is found just more often around the oxygen than it is around the hydrogen. So we end up with a partial negative charge because there's more electron density, we call it, around the oxygen. And we give that partial charge a lowercase sigma with a negative charge, and the partial charge on the hydrogen would be positive because there are less electrons around there. Remember, electrons are negatively charged, so wherever you find them, you get additional charge, negative charge density. And so there's a partial positive charge on hydrogen. So you can think about it, hydrogen has one proton in its nucleus, and if the atom were alone, it would just have the one proton in its nucleus plus one electron around it. Well, if we share that electron with oxygen, and oxygen pulls the electron away from the hydrogen nucleus, away from the proton, we're left with additional positive charge from that nucleus around the hydrogen atom. So if it's hard to envision the electrons being pulled and charges left behind, you can leave it simply in your mind as a partial positive charge on hydrogen and a partial negative charge on oxygen. And that makes a polar covalent bond. Okay? So, ionic bonds, nonpolar covalent, and polar covalent. I'm going to erase ionic bonds. We're not going to worry about those anymore today. Okay, we're going to talk about covalent bonds, both of the nonpolar and polar variety. And let's take an example, a simple example. Let's look at, up at the top here, I'm going to put it up at the top. Let's look at ethanol. All right, so ethanol is CH3. I'm going to draw out each bond. CH3, CH2. So there's CH2, and then OH. And I think I'll draw the oxygen in red, and I'm going to draw the hydrogen in black. Okay? So there's ethanol, CH3, CH2, OH. So I color-coded this for a purpose, because I want to talk about the fact that this part of ethanol, these CH3 bonds, these CH bonds, those are all neutral. Those are nonpolar covalent bonds. The electrons are shared equally in these bonds between carbon and hydrogen, and between carbon and carbon. So all these ones I'm marking as green right now, those are all equally sharing electrons. Well, what about the oxygen and the hydrogen? Well, the oxygen and the hydrogen are just like water. And that bond between oxygen and hydrogen shares electrons unequally, such that it ends up we have a partial negative charge on the oxygen and a partial positive charge on the hydrogen. So it's a little like water. So we have this nonpolar part of ethanol, and we have this polar part at the end. So one way we could draw it, I'm going to erase the molecular formula on the right here, and I'm going to draw the molecule just like this. I'm going to draw a little box like this. Let's color it in blue. That's going to be our nonpolar part. All right, so that part there is our nonpolar part of ethanol. And then I think I'm going to draw in, I'm just going to draw a circle here for the oxygen. And I'm going to draw a circle for the hydrogen. And if we wanted to put in the charges, we could say this oxygen is partial positive. So I'm going to put a little plus sign there. It's a little hard to see, but I'll put a little plus sign there. And then on the oxygen, here I'm going to finish coloring this in so it looks nice and pretty. And I'm going to put a negative charge on the oxygen. And remember, this is partial negative and partial positive. And oops, I jumped slides. Let's finish up that negative charge. All right. So this part here in ethanol is actually the polar part of the molecule. All right. Before I go on and talk about the impact of ethanol and the structure of the molecule on wine, I want to tell you briefly why we have the polar and nonpolar parts of molecules. In other words, why is it that if we jump back to water down here, let's go back to our water molecule, why is it that oxygen pulls electrons toward it away from hydrogen? And the answer is electronegativity. And that's an important concept in chemistry, and we won't get into it any more than simply what I'm going to tell you now. And that's this. Linus Pauling, the Nobel Prize winner, figured out that certain atoms attract electrons more readily than other atoms. And Linus Pauling came up with a scale, and the numbers here in this periodic table and the relative heights of all these bars, the numbers show the relative electronegativity. So if you look over here at fluorine, you see it's the most electronegative atom, 4.1 on the Linus Pauling scale. It really wants electrons. It attracts electrons to itself better than any other atom in the periodic table. But look who's second. Oxygen. 3.5 on the scale. Compare that to hydrogen. Hydrogen has an electronegativity on the Linus Pauling scale of 2.1. So there's a big difference between oxygen here and hydrogen over here. And because oxygen has a bigger electronegativity than does hydrogen, oxygen pulls electrons toward itself whenever it's in a bond with hydrogen. So if you have oxygen and hydrogen, the electron density, say we'll draw our electron as E with a little negative charge, the electron density is going to go toward oxygen, away from hydrogen, because oxygen is more electronegative. You can also look at carbon. Look at carbon down here. It has an electronegativity of 2.5. Hydrogen is 2.1. Turns out that's close enough to one another so that when you have a carbon-hydrogen bond, that is pretty neutral. The electrons are shared relatively equally because carbon with an electronegativity of 2.5 and hydrogen with electronegativity of 2.1, that's close enough that this becomes a fairly neutral bond with electrons shared equally. So this is neutral. The oxygen-hydrogen is actually polar because there are two poles. There's a negative pole toward the oxygen. Again, we have that partial negative charge. And hydrogen has a positive pole, that partial positive charge. And it's all due to electronegativity. So that's a pretty advanced concept in chemistry. I'm not going to test you on electronegativity, but I do want you to know that oxygen and hydrogen, that bond is going to be polar. All right? If you want to know more about it, down here at the lower left in this slide, I have a link to a Khan Academy tutorial on electronegativity. And if you just Google electronegativity Khan Academy, this will come up. And if you want to explore it more, you can go ahead and do so. What I want to do today is go on and talk more about the implications of these types of bonds for wine, and what the implications are for testing the levels of alcohol in wine. So let's look at a couple different scenarios. Let's look on the left here if we had just water in a solution. And look at, and I drew a bunch of waters here. The oxygen is the red circle, and the hydrogens are the black circles. So oxygens have that partial negative charge. Oxygens have the partial positive charge. So these are all partial charges, just to distinguish them from full charges. All right, so they're partial charges. And look what happens. Charges, opposites attract, and so a negative charge will be attracted to a positive charge. So if we have a positively charged, a partial positively charged hydrogen right here, and a partial negative charge on an oxygen adjacent, there's some attraction between those two. We call that a hydrogen bond in chemistry. When there's a partial positive on a hydrogen and a partial negative adjacent to it, there's an attraction there. We draw it with these bars, parallel bars like that. We call it a hydrogen bond. Well, and look at each one of these molecules. We can draw hydrogen bonds because we have opposite charges adjacent to one another. So look how nicely all these oxygens bind, or many of these waters, excuse me, bind to one another because they're aligned so that the opposite charges attract one another. Turns out water just lines up that way naturally because it can form all these hydrogen bonds because opposites actually attract one another. So it's pretty cool. So look at all that bonding that's going on in water. That gives water an internal cohesiveness such that if you wanted to boil water, you would have to heat it to 100 degrees Celsius. So it boils at 100 degrees Celsius. And boiling just means you've heated it up enough that these molecules are bouncing around vigorously enough that they're overcoming the internal attraction of one molecule for another, and they're escaping from the liquid into the gas phase. But you have to heat it up that high because there's so many of these hydrogen bonds in water. You have to get it really hot before it boils. Okay, let's look at wine. We'd have water and ethanol. So now I have a bunch of water molecules, again drawn the same way, partial negative on the oxygen, partial positive on the hydrogen. But I've thrown in that nonpolar part of ethanol, CH3CH2OH, that nonpolar part. So I've written the nonpolar parts in blue, or colored them in blue. Remember, they still have the OH on the end, so this is the OH at the end of ethanol. Again, it's CH3CH2OH. It's a molecular formula of ethanol. So we still have that partial positive on oxygen and partial negative on, negative on oxygen, positive on hydrogen. And that's a polar bond. So you have some attraction between that part of the ethanol molecule and waters. Look at that. They line up just like waters do on the left, and there's some hydrogen bonds. And there'll still be hydrogen bonds between water molecules, like there and there. And then there's a hydrogen bond here between water and ethanol. But look what gets in the way. All of these big nonpolar or neutral CH3CH2 groups, they get in the way. They get in the way of forming hydrogen bonds. So if this was just water on the right, like we have on the left, you'd have a lot more hydrogen bonds. Look at all the bonds on the left. We only have a few on the right. So it means water and ethanol just doesn't have the same internal cohesiveness that water does. It doesn't stick together as much. So water plus ethanol at about 14%, like we find in wine, it boils at about 90, let's say approximately 90 degrees C. So this would be wine boiling at 90 degrees C. Over here on the left, we have water boiling at 100. So kind of cool, huh? So that's what happens. And that big nonpolar or neutral CH3CH2 group, which has those nonpolar bonds, that keeps the molecules in wine from sticking together as much as they do in pure water. So that has implications for ebulliometers. So here's our ebulliometer. Here's how we test alcohol. And the way that this is constructed is we will pull out this thermometer here and we'll put our water or wine into this chamber. And we have a heating element down here at the bottom, our little alcohol lamp, and that just has a flame here that heats up the water. The wine actually flows into this part of the apparatus and gets heated by the flame. Once it boils in the chamber here. The thermometer's in the top of the chamber, and it records our boiling point somewhere on the scale. Over here in this chamber, we actually put cold water because as the alcohol boils, the pressure is going to build up. We need a place for it to escape, so it can escape through this tube here and come out the top. But we don't want it all boiling off before we get the be able to capture or read the boiling point. So we put cold water in here. This is called a condenser. And as the vapor comes up through the middle of the condenser, it'll cool off, it'll turn back to liquid, and it'll run back down into our chamber. And that's there only so we can keep enough of the liquid in our boiling chamber down here, keep it in there long enough that we can record the boiling point. It's a pretty cool little system. There's a little diagram over here on the right that shows you how it works. D in the diagram, that's our boiling chamber. So there's our thermometer. We take out our thermometer, we put our water or wine right down into this boiling chamber. And it shows the connection here with the heating chamber. So E would be the heating chamber. In this case, it might be electrical heat, or we could, in our case, it's going to be our little alcohol lamp with a flame, and that's going to heat our boiling chamber. Things are going to boil, and we're going to record the level on our the boiling point on our thermometer. A, this is the condenser, and so we'll put cold water in there. So it's a very simple little apparatus, but it's really cool. And then we boil water first. And remember, we had our little dial like this in class. And here, someone's boiled water, and they found out that based on today's air pressure, water boiled at 100.2 degrees. So right there. So that would be 100.2. And they set the dial so the outside zero is at 100.2. Then you go back to your ebulliometer, you dump out the water from the boiling chamber, and you'd add wine in the boiling chamber, and then you'd record the boiling point of the wine. Once you do that, you just go back to your dial, and the boiling point of the wine is going to be lower. Say the boiling point is 90 degrees C. So you read that on the internal dial, and then you see where it reads out here on the scale. And 90 degrees C, boiling point for the wine, gives you a 15.3% alcohol. So your alcohol would be 15.3%. That's how ebulliometers work. And the whole principle is based on the fact that water boils at a higher temperature than wine for all the reasons that we detailed here. All right, that's it. Thanks for listening, guys. Come back later. We'll have more lecture on sensory analysis. Have a great weekend.